Welcome you all for this 5 days ATAL FDP on Nanoscience for Nanomaterials. So at the outset, I should thank our management and principal for supporting us to organize event, for applying for such an event, and I should also thank AICT for granting us this event. So as we know, the novel topic on nanoscience is a very fastly emerging field. Though many research is going on by the science people, as an engineering department, we also would like to contribute more towards this field. Also, this FDP will be an initiative for such activities. So many from engineering colleges have joined here. 149 participants are here actually registered for the course, and almost everyone will be joining in a short time. So let us start this program with a small invocation song. So just wait a minute. Thank you. The program is organized by Manakula Institute of Technology, Puducherry. Due to the pandemic, we are not able to conduct it face-to-face. So we applied for face-to-face, but the AICT has asked us to go for the virtual mode. This institute is started in the year 2008 with 5 departments, and it has grown up with 8 departments in the consecutive years. And we have our head, Dr. S. Malarkan, principal of this institute. Right from the inception, he is here, and all the laurels and growth of the institute goes to him. So may I now welcome our beloved principal to deliver the welcome address. Sir, please.
Thank you, Armoli. So, respected chief guest of today's inaugural session of ATAL FDP organized by our institution, MIT, on the topic Nanoscience for Nanomaterials. Dear faculty members from our institution, and also faculty members who have joined in this 5 days faculty development program from various other institutions, and all the other participants who have joined. I wish to extend my sincere warm welcome to the respected chief guest and also all the participants who have joined in today's program. Welcome you all. I'm very happy to note that our institution is hosting a 5 days FDP program sponsored by AICTE on the very important topic nanoscience and nanomaterials. So the professor who is going to share ideas about this topic is a very renowned professor who has got a lot of credentials, research credentials, particularly on this domain. So we are very much thankful to Professor Satyanarayana, who has immediately accepted to join with us. Thank you, sir. So in today's scenario, the technological growth is very tremendous. So the faculty development is a very, very important component for the for any growing institution. If the institutions concentrate on faculty development, definitely they have got very good strength, not only in numbers and also the credentials. They have very good faculty strength. Only with the faculty strength and also the infrastructure support provided by the management, definitely that institution can do a lot of activities for the betterment of the students, including research. So in this aspect, see, in our institution, we are highly focusing on faculty development. We always insist our faculty members to do programs either through online or offline. We are sending all the faculty members very frequently to take part in this kind of activities which are happening in the other reputed institutions, so that they will get awareness on latest technological developments, and also they get in-depth knowledge on the latest technology, which can in turn be shared with all of our students, so that they can take up some innovative projects in these areas. So I think that, and also I'm hoping that this program, FDP program organized on this topic, nanomaterial, nanoscience, will be very much helpful for all the participants to focus on this particular topic, and also to take up some of the faculty members, they may be doing some research, so they can take one topic on this and they can do a lot of things on this. Okay, so I request all the participants, don't think that this kind of attending FDP program is only for getting certification, and with that certificates we can improve our profile, and we can apply for promotion, and we can ask for increment. It is not like that. It is only for upgrading our knowledge on the latest areas, latest technological areas. Okay, so what are all the information that we are gaining, knowledge that we are gaining through this program, which should be shared with your fellow faculty members and also with the students. With that information, we have to concentrate on research-oriented activities. So please attend all the sessions very seriously. Try to gain good knowledge in this area. Okay. So all the experts who are going to deliver various topics on various sessions in this 5 days program are the real experts who are working in this particular domain. So definitely all the sessions will be useful. So please attend all the sessions seriously. Try to interact well with all the experts. Definitely it will be useful. So with these few words, I once again extend my sincere warm welcome to all of you joined in this today's program. Thank you.
Thank you, sir. May I now give a brief introduction about the program. The session is scheduled from 9:45 to 3:30 every day. Depending upon the speaker's interest, it may be slightly extended. But we have scheduled 14 sessions. The first session will be by Dr. N. Satyanarayana, Professor, Puducherry University. And the session 2 will be shared by Dr. Dhaval Joshi, Project Scientist, IIT, Delhi, on hybrid nanomaterial technology for solar energy application. In session 3, Dr. Surjit Devanath, Professor and Head, Government Women's Polytechnic College, Tripura, and he is going to give a hands-on session on Python-based GUI, and he has planned a lot for giving a GUI-based interaction, so that it will be useful for researchers. The next day, 21, the session will be shared by Dr. O. Padmaraj. He is doing his third postdoctoral in Madras University. And the fifth section will be shared by Dr. Subhendu Manna, scientist, RUSA, Utkal University, on nanocrystalline ribbons for magnetic field sensor. The section 6 will be shared by Dr. Pradeep Kumar Panda from Yonsei, South Korea, on polymer nanocomposite materials. And once again on 22nd, Professor Satyanarayana will be sharing his knowledge on nanomaterials for dye-sensitized color cell applications, followed by Dr. Dennis Babu from Chettinad College of Engineering Technology. He has worked on the metal halide peroxide nanomaterials for advanced optoelectronic applications. The session 9 in the afternoon will be shared by Dr. Himadri Tanyadas. She is also a scientist in Rusa, Uttal University, on new advanced anode-free battery technology. The 23rd, the session starts with Dr. K. Venkatasiva, postdoctoral fellow from IIT Madras, on the role of magneto-electro-nanoparticles in biomedical applications. Then followed by Dr. Deepavar Majmudar from the chemistry department from Chandinagar College of West Bengal. Journey from supercapacitor to super capacitors. The session 12 will be a yoga session as per the AICD norms. So it will be headed by Mr. C. Panikumar, Director of LIYO Yogas, Hyderabad. In last session will be by last day. The session will be started by Dr. K. Hari Prasad, Associate Professor IARE, Hyderabad, on novel materials for gas sensor application. Followed by the second section by Dr. Himadri Danyadas on facile and cost-effective methods of generation electrodes. And the last session on 24th afternoon, we will have at about 2 o'clock, we will have a vote of thanks and the participants' words, and then followed by a test. So as per the norms, you have to attend 80% of the session. All the sessions will be recorded through the Zoom attendance. And each day you will have a feedback link at the end. There won't be any feedback link in between. So in the third session end, we will give a feedback link for each day. Okay, kindly join with the mail IDs that you have registered so that it will be easier for us to track the attendance. Otherwise, we have to get back to you. So with these few words, I think all the participants, the guest speakers are expertise in each field, and they are ready to share their expertise. So hope you all will have a good learning experience in these few days. Okay. So with these few words, I would like to call Dr. Vinod, my co-coordinator, who is really the backbone of this workshop for a faculty development program. I would like ask him to introduce our guest speaker and the session chair today. Vinod, please take it. Vinod, you are muted.
Sorry. Thank you, sir. So, a very good morning to the principal, sir, chief guest, convener, and the participants of our FDP program on nanoscience for nanomaterials. So, I like to say a few words and invite our esteemed speaker for the inauguration section. So, Dr. Satyanarayana, UGC BSR Faculty Fellow, Department of Physics, Puducherry University. So, Professor Satyanarayana has a huge experience in teaching of more than 31 years. His research area includes nanostructured, nanocrystalline, and nanocomposite electrode and electrolyte materials for lithium-ion, sodium-ion, and silver batteries, dye-sensitized solar cell, fuel cells, supercapacitors, sensors, and biomedical and dental implants applications. He served as HOD of Physics Department, Dean for Physics, Physical, Chemical, and Applied Sciences, and also a founder head for the Center for Nanoscience and Technology in Puducherry University. So he has 127 research articles published in various highly reputed international journals and presented more than 100 articles in different international national conferences. He has executed almost 22 research projects from different organizations of India, so Government of India, including DST, CSIR, DRDO, NRB, BRNS, AICT, CSR, and UGC. So he has guided around 21 PhD scholars. So with these research projects from Government of India, he has developed a nanoscience and technology research laboratory in Puducherry University, which consists of various synthesis, characterization, and fabrication equipments. So some of the equipments like vacuum pumps, pelletizers, vacuum oven, furnaces, electrical digital balance, density measurement setups, centrifuging machine, distilled water plant, rotary evaporator, ultra high frequency sonicated, ball milling, electrospinning, microwave synthesizer, cold isostatic press, 5 target DC and RF magneton sputtering, etc. So some other characterization instruments like PGDTA impedance analyzer with electrochemical system, electronic conductivity, transport studies, and thermoelectric power, battery fabrication characterizations, so which consist of Glovebot's battery life cycle tester, Bitrode, which is from the US, and silver and lithium-based primary and secondary batteries on pellet type as well as rectangular type. So he is also a reviewer for more than 25 international and national journals and a referee to various research project proposals submitted to DRDO, DST, CSIR, and DBT. So he is a lifetime member in 6 academic societies like MRSI, ISSIS, SAEST, IPA, IA, CG, MSI. So he also visited many foreign countries as visiting professor, which includes USA, Canada, Italy, Singapore, Malaysia for giving invited talks and attended many conferences at these various universities. So today, Professor Satyanarayana is also going to deliver an expert keynote lecture session, so which is on nanomaterial for lithium-ion battery application. Sir, we request you to give your valuable contribution to our FDP on nanoscience for nanomaterials. Thank you, sir.
Oh, thank you, Vinod. So shall I start or wait?
Yes, sir. Yes, sir. You can start.
So, one. So you are able to see the screen?
Yes, sir.
Hello. What about voice?
Yes, sir. Yes. Yes.
Both. Okay.
Yes.
Voice and screen is fine. Huh?
Yes, sir.
Nano materials to this participants of FDP program. So title of my talk is Nanomaterials for Lithium Battery Applications. So content of my topic would be, first I will briefly mention about various types of energy resources, and after that I will discuss about various synthesis methods, various characterization techniques for preparing and characterizing the nanomaterials for lithium-ion batteries. Finally, I will also discuss about fabrication and characterization of lithium-ion batteries. So we all know that among the available energy resources, fossil fuels like gas, oil, coal contribute highest, up to 87%. But they have two dangerous disadvantages. We all know that they pollute the environment heavily. Not only that, their resources are exhausted, so everything will be stopped. So there is a great demand for developing renewable and pollution-free energy sources. We have many types of renewable energy resources like wind, hydro, ocean, geothermal, biomass, batteries, fuel cells, solar, supercapacitors, etc., of which we develop nanomaterials for lithium silver-ion batteries, solid oxide fuel cells, etc. Today's topic will be nanomaterials for lithium-ion batteries. So, how do we develop the nanomaterials? So, through our research activities, we develop the nanomaterials in 5 different phases. Nanomaterials, of course, and devices also. The first phase So we investigate various types of synthesis processes. So we have developed more than a dozen methods to develop the various properties of nanomaterials for different applications. Starts with the solgel, melt quenching, conversion, polyol, etc. So more we will try to discuss in the next session. So second phase, actually characterization. We use XRD, FTIR, DSC, the intermediates as well as final products. By characterizing the intermediate product, we not only monitor the synthesis process, but also optimize the synthesis process conditions. Then by characterizing the final products, we will be finding out the property of the prepared materials. Then third phase, microstructure and properties. We use scanning electron microscope or transmission electron microscope with EDX, energy dispersed X-ray spectroscopy, TM. So we use these two techniques to characterize the intermediate and also to characterize the final product to find out their microstructures. And UV visible VSM and implant spectroscopy we use respectively to find out their optical, magnetic, as well as electrical properties of the final product. Actually, from electrical properties, we decide or pick up the particular material for particular applications. Then fourth stage, once you pick up the material, then you go for device fabrication and characterization. So in that we design and fabricate the and characterize the various types of devices, batteries, DSCs, fuel cells, supercapacitor, etc. So today topic will be on batteries. So 1 to 4 phases, every PhD scholar has to do. So it is a compulsory. And fifth phase, actually, it is option depending upon the student's interest and capabilities. Some students develop the electronic circuits. Some students develop the equipments required for their research. Some students develop simulations of the. So that's why this is fifth phase is option for the students. So we are all these techniques we have developed in our laboratory for starting from glasses, bulk material to polycrystalline, to the in this is sputtering. Actually, initially we were using those 3, and now finally
Professor, sorry to interrupt you, Professor.
Technique to develop them. Then yes.
Sir, you can switch off your videos. I think the bandwidth is not sufficient. It's buffering.
Okay. 1 minute.
Your voice is breaking.
1 minute. Actually, there is 1 minute. Oh, now it's fine.
Yes,
Hello?
sir. Yes, sir. You can continue, sir. Now your voice is clear. Yes.
Oh,
1 minute. Now it is clear, huh? Okay. chemical energy into electrical energy by means of redox reactions. That is, oxidation and reduction reactions. It will convert the chemical energy into electrical energy. Oxidation takes place at anode and reduction takes place at cathode side. Then we have two types of batteries. Primary, once you discharge, you have to throw it because reversible reaction is not possible practically. Okay. And the second type is secondary batteries where reversible reactions are possible. So you can recharge many times, like cell phone and laptop, etc. batteries. So we have different types of secondary or rechargeable batteries like lead acid, nickel, cadmium, nickel metal hydride, and lithium-ion battery. So of which lithium-ion batteries exhibit highest energy density. So we developed the nanomaterials for lithium-ion battery application. So if you look at any battery, anode, electrolyte, and cathode are the main parts of the battery. So we develop the materials with the different properties useful as anode, electrolyte, and cathode for various types of energy device applications, like silver lithium-ion batteries, solid oxide fuel cells, Nanoscience solar cells, and supercapacitors. So some of the primary batteries of lithium and silver developed initially in our laboratory, and later on secondary batteries, prismatic type, button cell type. Now we are developing thin film lithium-ion batteries using RF and DC sputtering. For improving the lithium-ion battery technology, there are many issues and challenges. Most important issue is safety. You can see that so many laptops and other electronic gadgets getting fired due to explode of batteries. So you can see that about 10 years back, many it were happened actually. Now, recently, nanostructured materials are found to be better candidates than their respective bulk counterparts in terms of not only safety, but also they showed the improved energy density. So this next slide follows the statement justification. So here you can see that battery is made up of the bulk, battery is made up of the nano materials, and both the characteristics are given here: cell voltage versus time and cell temperature. So when you are recharging any battery with time, cell voltage decreases, and due to the redox reaction, cell temperature also increases. You can see that red one is cell temperature, black one is decreasing of cell voltage. At particular temperature, you can see that when it reaches a particular temperature, so battery catches the fire or explodes. So that's why you can see that there is a sudden increase in the temperature. And similarly, here also the battery with nano, here also cell voltage decreases with time, and also temperature of the cell also increases. But here, since it is made up of the nano, so it withstands. So there is no smoke or fire or explosion. So that's why if you develop the battery with nanomaterials, so safety of the battery will be improved. And also later on we will show that not only safety will be improved, and energy density of the battery also will be increased. So now we will try to discuss about the various synthesis methods for preparing the nanomaterials. So as I said, actually, we use the soil gel process maximum for developing more than 50% of our materials, and also some rare other materials, combustion, polyol, hydrothermal, co-precipitate, micro, sono, chemical, microwave heating, electrospinning, etc. So we will try to discuss some of them here. All may not be possible, but I think 5-6 techniques methods we can discuss. First, we will start with the sol-gel process. So the sol-gel process, okay, involves about 7 steps to develop any material using the sol-gel process. The first one is mixing, is the most important one. So here mixing is done through hydrolysis and polycondensation reactions. So hydrolysis reaction is, for example, if you want to prepare the SiO2 material, so you have to take the starting material, or we call it a precursor. Here precursor is taken as a alkoxide. So alkoxide is it can be a here this is called tetraethoxy. Okay, alkyl orthosilicate actually. So here R can be a methyl or propyl or butyl, etc. So here we take the butyl. So tetraethoxy orthosilicate we have taken. So we have a then this is hydrolyzed with water. When you hydrolyze with water, okay, alkyl group will be removed and hydrogen will be substituted here. You can see that 1 hydroxy is one of the 4 ORs will be removed, and here it is hydroxy. Then 1 mole of alcohol is removed. It can be 1 mole or 2 mole or 3 mole or all 4 also. Here, this is the first one, and the 4th one is, you can see that here all 4 alkyl groups are removed. So 4 mole of alcohol is removed here. So that way you can get any 1, 2, 3 or 4 reactions can take place simultaneously, and this can be monitored through NMR exactly how many single type reaction or 2 types or 3 types or 4 is removed very clearly, can be monitored using the NMR technique, which we did. I did 20 years back actually in USA. So now these molecules again, they react with 1 or 2 or 3 or 4 and form the breaching. So next is condensation reaction. You can see that 2 molecules join together by releasing the water. So oxygen bonding SiO bond, okay, network is formed and by releasing the water. So this condensation reaction progresses at 3-dimensionally, and forms the gel actually. So here you can see this single one can be, or 4 can be, 3 can be, 2 can be. All reactions will occur simultaneously. Finally, with time, so condensation progresses, 3-dimensional will become polycondensation reaction. So that's why mixing and hydrolysis and polycondensation reaction, one can build a 3-dimensional SiO network. And now next slide shows that 3-dimensional network is shown in the form of 2D picture. Actually, you can see that SiO. So this way, and 3D also it will go. So during this polycondensation reaction, not only network is formed, all unwanted things will be pushed to the end. Either it will be alkoxy or hydroxy or any one. Other unwanted solutions will be in the network moiety of here. Okay, here actually. So now after forming this will be in the form of, and then this size of the moiety can be varied, smaller or bigger, depends on the required property we need actually. So that can be done through different conditions actually. So in this, so these unwanted things should be removed to get the pure SiO2. So what we do is first to evaporate these unwanted solutions which exist in the pores. So we do the aging. So aging will be done. So then through aging, this will be gone. Then after aging, then, oh sorry, after aging, so unwanted solution will go off. Then there is increase in the bond strength between S and O, Si and O, compared to O and H or O and R. So what happens actually through control heating, so hydrogen and alkyl group will be removed. Removed through what we call control heating. So when you do this, you will get a pure SiO2. So this way you can get any type of materials. Fortunately, our students could do almost all the available materials by any other technique we could develop, starting from 0 dimensions of quantum dots, 1 dimension of fibers, 2 dimensions of thin films, spheres, grains, powders, bulk of 3 dimension, different shape, 3-dimensional materials. So 0 to 3-dimensional materials we could develop in our laboratory under different conditions. And all these dimensions can be ordered and disordered material and bulk and nano materials. We could do it. Not only that, highest density materials, aerogels, we could make it for fuel cell applications, and ultra low density aerogels. Aerogels means actually their density is actually 2% higher than the air. So aerogels, super thermal insulating materials we have developed for one company to Boston, one company. And so aerogels we have developed, and aerogels also highest density for fuel cell applications actually. And of course, these other materials like glasses of thin films or bulk or fibers we developed using this one. So this technique, Sol-Gel, okay, since we are able to, one can develop a variety of materials, whatever you think you design, you can get. So this technique, American Chemical Society is named as a tailor-made method. So tailor means actually you can see that if you give one cloth to the tailor, so depending upon his capabilities, he can stitch varieties of designs for ladies, varieties of designs for gents with the same cloth. Similarly, here also, if you know the science of the chemistry, you can design whatever the property you need in any phase of the material using this, any dimension of the material using these soldiers. So that is the one. So fortunately, we could do almost all these things mentioned by developing various types of conditions and all using soldier process. That's why we could develop more than 50% of our materials actually. Now I will try to discuss the synthesis of nanoparticles and nanocomposites using soldier. Nanoparticles usually they have a tendency to aggregate because of their surface properties, surface and charges. So it's difficult to study the nano size of it. Okay. So what normally you do is if you want to do individual, so you try to make the nano composites. You disperse in one insulating, so you can study the individual particles, or you want combined agglomeration type you can do, or you can do coating of the materials this way, or you can do core shell type. So coat the nanomaterial over the insulating or insulating material over the your required compound actually. So these we call core shell type. Anyone, whatever you like, you want to particular application, you can design and you use a little science of the chemistry and you can develop required property materials. So this can be done under acid catalyst or base catalyst. So both you can do actually. So you know acid catalyst means actually low pH. So reaction is slow, so you can get the bulk. So reaction will be longer actually. Base catalyst is high pH, reaction is very fast, so you can get a fine particle. Oh, this way actually. So now we will try to do one by one. So this is the one actually under acid catalyst. So here, actually this paper has got so much citations actually, and this took about 6 months by one PhD scholar and postdoc actually, and this has given a lot of good citations actually. So what happened here? We have developed two nanocomposites. One is nickel aluminate nanoparticles dispersed in SiO2. Second one is cobalt nickel aluminate nanoparticles dispersed in SiO2. So to make it SiO2, we use the tetrahydroxysilicate and hydrolyze with water. So this is the one we get a clear solution. Then to make a nickel aluminate, okay, we have a nickel nitrate, aluminum nitrate. We make the solution, and since they can dissolve in water, and if you want to dope the cobalt, so you add the cobalt nitrate. So this is a clear solution. This is a clear solution. So both of them you mix your solution and sell it. You also get the clear solution, which we call it. So all colloidal solution. So this colloidal solution, okay. So hydrolysis and condensation reaction progresses. Then with time, when you cast it in beaker or any required container, so it will form the gel. Once it forms the gel, then I said, no, you dry it. So aging is done through drying actually. Once it is dried, this dried gel, we call it intermediate. So we characterize here also, in every stage we monitor through XRD and FTL and DSC. So that time it was not, we do not have a DSC or TGDA, but we could make it XRD and FTR. In fact, this experiment made us to buy TGDTA because it is a very essential for monitoring this synthesis process. So once it dried, so you do control heating. When you do the control heating, then you can get a nickel aluminate dispersed nanoparticles in SiO2. So these block spheres are nickel aluminate or cobalt nickel aluminate, and gray background is SiO2. So how do we know that this is a schematic, but how do you know that this can occur and how do we monitor? We will try to see the next one. So you can see that I have not given the IR, but XRD is enough for this. So we have taken the XRD. For every stage, actually, it was the soil is prepared at 60 degrees centigrade, so or 30 degrees Kelvin. So when you take the XRD of this one, it is amorphous. So all are in iron, whether it is silicon or oxygen, nickel or aluminum, all are in iron state. So you don't see any solid structure in this. Increasing up to 800 degrees centigrade or 1073 degrees Kelvin. So this complete gel is in amorphous. Only at 800 degrees centigrade, that is 1073 degrees Kelvin. So some peaks start coming actually, and they grow with increasing the temperature. So crystallization takes place. So when we analyze these things, they are actually okay. They are in the nickel aluminate phase. So crystalline phase of nickel aluminate is one. So thermodynamics. So this much 800 degrees centigrade is required to form the ions into the nanocrystals or nucleation stars. Nanocrystals of nickel aluminate. Then crystal growth occurs and this one. So this is what actually we confirm that nickel aluminate. Similarly, cobalt nickel aluminate also monitored actually. Now next, this is the one we confirm from this. We also see directly from the TEM. Now we can see that. So 10 nanometers, okay, range we have taken nickel aluminate. So these block spots are the spherical nanoparticles of nickel aluminate. Gray is the SiO2 amorphous. So here, cobalt nickel aluminates are in the range of 5 nanometers. you can see that spherical particles of cobalt, low particularly nanoparticles. So this is published Journal of American Ceramic Society, and we also did so many other nanocomposites. Here we have grown the in situ cobalt ferrite nanoparticles in SiO2. This is published in the French journal, different student action. Okay, so like this we have made so many. So finally we say that the developed nanocomposite is this way. So nanoparticles dispersed in SiO2. That is nanocomposite. Okay, see like this you can get a variety of compounds actually you can do in this way. So next one is when you use the base cat. So you can do using the acid catalyst many varieties of nanoparticles or nanocomposites can be. So we usually if you make a pure nanoparticle, they will be agglomerated type. Okay, because of its nature. So now we use the base catalyst assisted growth. So base and also you have to use ultra high frequency sonicator. So when you do that, base catalyst means high pH. When you do the high pH, under high pH, reaction is very fast. And when reaction is occurring fastly, then keep the soul under the high frequency sonicator. So for every reaction, okay, it removes the formed the particle, so you can get the fine particle. So this is the one developed by one student. Complete thesis is done on base catalyst assisted growth using the ultra high frequency sonicator. So now you see this. So this is the schematic diagram, and this is the ultra high frequency sonicator. Same thing here also. You take the SiO2 for making SiO2 tetraethoxysilicate and the alcohol, and it is hydrolyzed with water. So only thing we change is instead of acid we use the base, ammonia hydroxide. So when you use the base, okay, fast reaction takes place. So this beaker will be kept under this spindle. So okay, then what happens for every reaction? So particles will be separated actually. Formed particles will be separated. So this way particles will be forming. So if you want to coat any oxide to this particles, actually what you do is we add okay, metal precursors, whatever you want to add actually, whatever you want to coat, whatever you want to substitute actually. So when you do that, so this is the one you will get coating. So resin will be coated over the particle. So then when you calcinate, okay, the coated particle, unwanted things will go off, particles will be coated over this thing actually. So in this calcination, particles nanocomposite can be formed like this. That means nanoparticles coated over the SiO2 or continuous coating of the nanomaterial over the SiO2 or SiO2 coating over the nanoparticles of required one, actually, whatever the thing. So either one of them can be. These two are called core cell type actually, and in this we could make it this way. So we will try to see whether we are able to produce any one of them using this process, using the base catalyst. So now for that we have made the first cobalt ferrite solutions. Okay, solutions. Then TOS solution. Okay, TOS sol and cobalt ferrite solution. So these two are TOS solution. Then when you mix with cobalt, then you get one. When this gel is calcined or fired, then you may get. We got this type of one. So this is the one we make it actually. Now we will try to confirm. These are the direct pictures of solutions. When you make a cobalt ferrite, this one, it will be like this. When you make the TOS sol like this, and finally we are expecting this type of nanocomposites. That is, there is cobalt ferrite nanoparticles coated over the SiO2 particle. So now we try to do pure one SiO2, what it is. So pure one, when you take the XRD, so you can see that it's amorphous. So SiO2 is in amorphous phase. So what is the particle shape, microstructure? So you can see that highly homogeneous spherical particles of SiO2. So when I will be able to say SiO2, then you do the EDX, energy dispersive spectroscopy. Then you see that what are the elements inside the sphere. So here is the EDX. You can see Si, silicon and oxygen only. No other peaks are appearing. So these particles are purely SiO2 and they are in amorphous form, disorder form. So these are the elemental analysis and direction. So what we prepare this SiO2 is the pure SiO2 with amorphous phase. Okay. Now we try to add cobalt ferrite to this. So we will try to see next one. So if you take the XRD, you can see the previous one completely amorphous. Now next one is you can see there are peaks. So when you analyze the peaks, actually crystalline peaks, they are due to cobalt ferrite. So cobalt ferrite nanoparticles exist in SiO2. Of which form we will try to see. So then you can see this this SiO2 coated. You can see white dots. So magnification, you can see that. This SiO2 over that you can see these dots. These dots, when you analyze it, actually they are cobalt ferrite. So you can see that previously EDX, energy dispersive spectroscopy spectrum consists of only silicon and oxygen. Now you can see that apart from silicon and oxygen, you have iron and cobalt. So definitely this is the nanocomposite. So you can see that the cobalt ferrite particles are not continuous, it is deposited. So now from this we can understand the form of the nanocomposite is this microstructure. So that means nanoparticles of cobalt ferrite coated over the SiO2. So they are cobalt ferrite nanoparticles are crystalline, polycrystalline, and SiO2 is amorphous. So it is nanocomposite form. So whatever we propose, we are able to get this type of nanocomposites microstructure compound. The next one is you can do core shell type. You can see that. Okay, so lanthanum oxide is coated over the cobalt ferrite. So this way you can get this one. So like this you can do vice versa also. So depending upon your requirement. So this they want to have a cathode material coated with lanthanum and they are confounded using the SAD pattern of the term. So you can see there the values are exactly matched. So then like this, using acid and base catalyst, we are able to prepare bulk and nanoparticles, fine particles, nanorods, nanoporous, nanocomposites, nanocoatings, and so many varieties of compounds we are able to see. You can see that nanofoams and nanoflowers, like different types. So size of the flower is micron size and petals are nanometer. So this actually helps to have a good mobility and good conductivity, and this will help to improve the what we call battery properties actually. So different students have done different types of materials for their PhD works. So initially we were doing the bulk glass electrolytes using the solder process. You can see the bulk and different colors actually of materials retained. So with that solder This is lot. Okay. So acid and under base 2 we have seen. Next one is combustion. This is also more famous one. This is also very good method to develop different types of nanomaterials actually. So we here actually basic is actually if you add any two elements, okay, directly what happens actually if a chemical reaction takes place fast, then you can get the bulk material actually. Now you add the reaction rates, reduce the reaction rate, then you can kind of make the, for that you try to chelate the ions apart, so you can reduce the fast reaction then to get the fine particles. That is the concept. For that you can take a, you have to take a, you have to do indirectly take a one low temperature, low melting, boiling point compounds actually. So mostly polymers. So either you take a monomer or polymer. Monomer means you polymerize, or take the polymer, you dissolve it, polyacrylic acid and ethylene glycol you take. So both this will be, we have a branch type polymers and parallel linear type actually. So when it is linear, so holding of the compounds will be less. So to make a branch type, so what happens actually polyacrylic acid and ethylene glycol, this one is a polyacrylic acid. So these two are, when they combine, they form the branch polymers. So this continuous is the polyacrylic acid, this is the ethylene glycol actually. So you have a one moiety, under the moiety you will have a unsaturated oxygen. So wherever there are two oxygens are there, cobalt 2 plus is entangled, wherever single unsaturated oxygen is there, lithium ion. So like this, every moiety you disperse the ions of cobalt and nickel, because I want to prepare the lithium cobalt oxide, lithium ions and cobalt actually. So for that you are taking a lithium nitrate and cobalt nitrate. So these, when you make this resin, you try to disperse the lithium nitrate ions and cobalt nitrate in this fashion. When you do this one, I have shown the one moiety like this, you will have a n number of moieties is the polymer chain. When you do this one, this is the one resin. When this resin is dried and intermediate you get, then you try to calcine when it is fired at 450 degrees centigrade, this polymer will be evaporated. Only ions will be there. These ions will form a lithium cobalt oxide. So in this moiety, very less number of atoms will be there. Due to that, you will get the fine particles. In this one, in this moiety, different particles in this water. Like this, you will get a different number of particles. Okay, fine particles in the nano size you can get. So this is the schematic chemical reaction mechanism, and finally you can use the temperature direct one. You can see the nanoparticles formation. Suppose you want to coat any insulating material for better applications, actually you can do that also. So here you can see that aluminum oxide is coated over the lithium cobalt oxide, the cathode material. For this, what we have taken is, we have taken the polyacrylic acid and ethylene glycol. We form the resin. In that, you disperse the aluminum nitrate. You disperse the aluminum nitrate solution. When you disperse, you can see that aluminum has a 3 valency. So it is entangled with the 3 oxygens. 3 oxygens. So it is like this. You will have so many moieties. So this is the resin is formed. This resin, in this resin, whatever you prepared the previous process, lithium cobalt and nanoparticles, you try to disperse it. When you disperse it, each nanoparticles will be coated by this resin. So this resin is polyacylic acid and ethylene glycol and L. So now you can see that. So this is a structure. This whole thing is resin. This is a lithium. So like this, every nanoparticle was coated with resin. So when you, every nanoparticle is coated with resin. So this polymer resin, when you fire it, polyacylic acid, ethylene glycol will be evaporated, nitrate also evaporated. So left out is aluminum and oxygen. So these two will form and coating over this. So you can see that coating over the lithium cobalt oxide nanoparticles. So this is the, we can do nano coatings. So 1, 2, 3 or 5, maximum 5 nanometer size of coatings you can do. So this, again, this schematic diagram is confirmed directly from the temp. So you can see that this is the temperature of lithium cobalt nano particles, cobalt oxide nanoparticles. To this, we have coated the resin. This is a resin. So this is a resin, is the one. Then when it is fired, so polyacylic acid and ethylene glycol is gone. So aluminum and oxygen is formed lithium, aluminum oxide over the lithium cobalt oxide nanoparticles. So this is a nano coatings. So we have developed this resin coating technique for surface modification of any nanoparticles. So this can be extended to a variety of compounds. So then this is what actually I showed the output with the schematic. Now direct one is this. So direct one actually, so you can see that lithium cobalt oxide solutions are prepared under different conditions as acetic acid, glycine, and urea. Okay, transparent solution, resin formation, drying polymeric intermediate, calcining, and finding out the lithium cobalt oxide. So under different conditions, acid, nitrate, glycine, and urea, which one will be better? We optimize the process. Okay, so this is the flow chart. Then we will monitor this one, how to monitor and how to optimize the reaction. So before that, you can see this is a direct observation. So lithium nitrate and cobalt nitrate mixed solution looks pink color. Then you stir it and heat it. So unwanted things will go up. This solution gets polymerized. So resin is formed. So during this, so unwanted gases, nitrates will, when they go off, it gets buffered. It gets buffered actually, because when resin is stepped, okay, like a bread, it gets buffered. So because of unwanted nitrates, when they protrude and goes off, so you can see that this is called intermediate. So buffered material intermediate is like this. So from this solution to this one, we get intermediate, and this also we characterize XRD, and microstructure is SEM or TM actually we do. When we do from TGGTA, XRD, FTIR, SEM, when you take, then we can study this intermediate and optimize the process. How we do it, you can see this. So the same compound is done under acetic acid, glycine, and from this itself actually, okay, from the experience we'll say that this is better. And how do we confirm? We confirm from first TGGTA. TGGTA, you can see that. So this gives the single peak, whereas these two will give multiple peaks. So from this itself we can understand. Okay, multiple peaks is good, and single peak is. So if at a time if an exothermic occurs, that means actually at one particular temperature, all unwanted polymers will go off. So left out ions will form the pure compound. So pure phase actually. That's what we observed. Observed XRD and also FTR. So FTR also you can see pure compound. Whereas when these things are there, one part is increased, so something is formed. Again, one part is evaporated, some other complex. So you can see multiple phases, multiple structures. Okay, multiple structures. So these are not good. So this is only good. And fine particle and pure compound. So from this we can understand. And same pictures also we can see why this gives you only one single exothermic peak, while others are giving more than one. So you can see that this is actually like a pores are less, but they are like a higher flakes type. So easy to burn. Whereas here pores are very high, you can see that very pores are very big, is much bigger. Okay, because that nitrate, okay, it will come out this one, but their walls are very strong. You see that walls are very strong. Okay, this is stronger than this. Actually. That's why you can see multiple reactions or multiple exothermic reactions. So that's why, okay. So because of this structure, so it has a multiple. Because of this microstructure, it has a single one. So at a time it goes on. So this is acetic acid is taken as a better one for developing the lithium cobalt oxide nanoparticle. So we optimize with that and go for further. Then similarly, we have developed nano rods of lithium manganese phosphate. So this is a very good material for lithium battery applications. So you can see nano fibers of nano rods and carbon coating nano rods. You can see that. So their coating, carbon coating is 2.3. You can see temperature. This is a carbon from the elemental energy. So this is on lithium manganese phosphate. So this is published in Journal of Chemical Society. Okay, so that is the one combustion and polyol. See, other one is microwave hydrothermal. So this is actually pure, okay, direct physics. Okay, the electrical engineers or physics people can understand better way than any other science people. So here actually only one condition is whatever material you involve actually either solvent or solute should be in a position to should able to absorb the microwaves. When they are able to absorb the microwaves, then okay, it is possible to do microwave still hydrothermal with that material. Otherwise, if they are not, okay, they are not absorbing, so we cannot use the material for this microwave synthesis. So we have developed the iron oxide, porous type of iron oxide actually. So what happens actually when you dissolve this one, so iron and chlorine ions will be will be forming in the solution. So these ions absorb. So okay, solvent absorbs the microwave and gets energy. Those things okay, will get a moment of ions actually generate the heat because of the friction. So that heat energy is sufficient equivalent to the okay, but we have heated directly in the combustion process. So then you get a reaction takes place then under particular conditions. What are the conditions you develop? So okay, similar. So accordingly, your compound will be forming. If you add a directional okay type of aid, then you can change the okay shape of the magnet. So here it is a sphere type of porous. And next one we have seen actually rods. So under rods actually, and this is the one microwave hydrothermal synthesizer actually from here. These are the MnO2 nanorods. So how they are made actually you can see that. So if you want to do MnO2 nanorods, okay, manganese state is taken and Sodium persulfate is taken as a direction growth material, or we say that capping agent. Why capping agent we call it? Okay, when this gets polymerized, okay, these polymerization takes one dimension. So this material will not allow to polymerize in all directions. So it will get entangled in all the other direction and grow. So polymerize in one direction. So that way, actually, this is we call it a capping agent. It caps the reaction direction. So you get this one. Then when you heat it, actually, the unwanted things will go off. Then manganese oxide nanorods are formed. Nanorods are formed. Then we add lithium hydroxide to this nanorods and do the solid-state reaction. Just heat it. What happens? Lithium gets diffused into this, forms the what we call lithium manganese oxide nanorods. So we have developed this one spherical nanorods under different conditions using this microwave hydrothermal method. So you can see the spherical and rods, etc. You can see the spherical small type rods, mixed one, pure one, etc. You can get iron, lithium manganese phosphate, and the lithium manganese oxide. In different things and different shapes actually. And here SNO2 nanoflowers, nanoflowers and nano sheets. So these nano sheets are nano sheets are like nanoflowers are very very useful, and they can enhance the capacity of the battery, like anything that is due to nano structures, that is a dimensionality of a dimensional, because it is a sheets. Okay, the movement of the ions will be the shorter distance, faster, and conduction will be very high. So you can get the better capacity material for nano sheets and nanoflowers. So under different conditions, you can get the nanoparticles directly if you use citric acid sheets, ascorbic acid to make it this one. So actually they direct the formation, polymer reaction formation. So that helps to change the what you call microstructure of the nanomaterial. So that way you get a hydrogen. So now we have developed the ultra low density materials called aerogels. So T is SiO2 aerogels we have developed. For starting material is same. The precursor is same. Tetraether orthosilicate hydrolyzed with water. Okay, hydrolyzed with water. Hydrolyzed with water, and hydrolysis and condensation takes place to get the three-dimensional picture network of SiO2, and it is shown as a two-dimensional. So when you brush it, alkyl or hydroxide hydrogen or they become unsaturated. You can see that outermost oxygens are inner is fine. Inner is actually they are neutral, but outermost all oxygens are unsaturated. So they are hydrophilic. So they react and absorb the moisture, water, moisture, and become watery. Okay. So what we do is we do the surface modification. Surface modification with only one of them. We did trimethyl chlorosilane actually, and we took this trimethyl TMCS, trimethyl chlorosilane. When we take this one, so this hydrophilic nature into hydrophobic. When you make the hydrophobic time, so it will be forever actually. So they will not get disturbed. So you will get a. So we made 2008. Still it is intact actually. So nothing else. So more than 13 years actually over. still we have a good quality aerosols are having in our laboratory. This we did for one company, Boston company. So you can see that aerogel made this one actually it absorbs and it goes to the bottom of the water. So this is the aerogel. Now you do with the TMCS, okay, TMCS, surface modification. So what happens actually is, so then, okay, because of this, all unsaturated oil becomes saturated. Okay, then you can see immediately this aerogel has become hydrophilic to hydrophobic. Comes. So it will only float, it will never take any water inside actually. Okay. So now these are the things actually in our laboratory when we develop the bulk. This is a bulk gel, alka gels actually. Alka gels, okay, it's prepared under various conditions. So these aerogels. So sol is actually, I said, a colloidal solution, clear solution, colloidal. They will be into nanometers, so you will not see anything. These things in the use the gel, then network will be formed. So this network, without is forming with a single atom brick, single brick, a network. So what happens if it is a bulk, high density? What we do is, so we remove when we are remove the unwanted things, these gets condensed and become high density. And in terms of aerogels, in this case, without shrinkage of this network, you remove the unwanted things. So that's what you do under supercritical or under different conditions actually you do. So you remove the unwanted things and get the almost same structure of this one actually. So that's why what happens. These aerogels will have a 2 to 10% higher weight than the air. So that's why they are aerogels actually. So some of them we did actually. So this is from intermediate to final different conditions. So okay, blue or transparent things are good, but yellow and other things are not good. So different conditions they made. So we developed bulk type and beads type. So beads, aerogels and bulk aerogels. One Boston company actually they want. So you can use this one. So actually advantage is the advantage is if you can make something will happen. Or okay, nothing will happen. So they act as a and insulating, thermal insulating materials. So that is the one people have tried, tested up to 550 degrees centigrade. So up to 550 degrees centigrade, so nothing happens because this is made up of SiO2. So this way you can see ultra low density and for an electrolyte for a fuel cell, they need to have a higher density. So we developed the lithium silicate electrolyte in solid process, highest density material. So they require highest density material for that. So ultra low density is harder glasses, these are the we are prepared to think. So yes. So we did few methods and characterization. So we'll go for fabrication of and characterization of lithium batteries. So this is the one actually prismatic type lithium batteries, secondary batteries developed in our laboratory. So we have taken 2 electrodes. One is lithium foil as anode and aluminum foil for the cathode. So whatever the cathode material we developed, we made the composite and coated over the aluminum foil. Then afterwards, this was wrapped with covered with separator because these two should go inside the container. So when they touch, actually shorting occur. So to avoid shorting, we insulated, we covered this one with separator. Therefore, a separator and permeability, electrical contact will not be there. So once you made these two, then put them, take the container, in that you put a electrolyte, then put the anode, put the cathode, then these are the things. These are the leads. Okay, so then you characterize this one. Charge, you will see the charging, etc. Whatever the characterization technique is involved, so you do it and find out its properties, study the anode and cathode, okay, and give the final product properties of the battery. So now this is what actually we have done nanofibers. Okay, nanocomposite polymer using the electrospinning technique. Okay, and technique we have done, and this is the one separator. So this is the lithium ion battery fabrication. So we take the cathode material, okay, and mix it with all conducting electrodes. Then slurry, then this slurry use the doctoral. Then required after drying actually to make the required shape of the cut the required shape of the material actually and after press. So this is called positive. Then nanocomposite is polymer, nanocomposite polymer. Okay, nanocomposite polymer is electrolyte, and negative electrode is actually so anode, electrolyte. Sorry, this is anode, electrolyte, and cathode. So 3 together form the battery. So here it's color, but all these things should be done, carried out under a dry box actually. So for that we need argon atmosphere. Completely this ultra high purity rather spectra pure argon will be passed to the inside this so this is one phase called this fabricating the lithium button cell type lithium ion batteries. And there is a button cell or prismatic type. Any one should be done under dry condition. So actually here we do 2 types actually, or okay, button cell type actually. So here, here actually for this you require 5 items. Here about I think 3 plus 4, okay, 7 items actually. So Swaziland actually can be usable actually. Here also we cannot reuse actually, it's very costly. So we may do final product with this. So for all characteristics, we do Swaziland. Okay. Final one. The elements we use all in order, totally about 10 elements in the concept to get this about. This one is just assembling, make it. And then afterwards you try to measure the air voltages, open circuit voltage. Then you can see that when you do the charge-discharge characteristics, the polymer electrolyte, nanocomposite polymer electrolyte developed in our laboratory by a student is showing better properties than existing commercially. Okay, so you can see this. So same thing when you are showing has developed the anode material. So this is the one theoretical capacity of the graphite. So about 400 something actually, then you can see the anode material of iron oxide anode material, nanomaterial showing better capacity than the available, commercially available lithium-ion battery and their charges. Here through nano coatings, we are able to improve 30%, 35% improved capacity. We could do, this is called lithium manganese phosphate. 2.3 nano. These are the primary batteries for all power applications. You can see that running the calculator or the OIS, everything we did beginning maybe more than 20 years back. We did beginning now most compounds are second. And that to material cost and so for that thin film technology. So you look at the thin film lithium battery technology. So there is a great demand for developing miniatures to provide energy for the increasing miniaturization of electronics. So electronic devices are smaller and smaller, so they require miniaturized energy to run the electronic circuits. So advantage of thin film process, thin film batteries can be manufactured using the same techniques as the microelectronics. So whatever the thing is, so if you develop the process, so you can use the instruments, instruments what microelectronic industry uses actually. With that you can develop, you can manufacture the thin film. By doing thin film, what is the other advantage you can get is, so you don't have to develop a separate new one. So advantage is the deposition is done under a vacuum. So you can avoid the moisture problems. Very good addition will be there between the layers. So contact will be less in this, so you can get a better. Yes, this is why electrolyte patience will be minimal. So whereas indirect bulk, however you make, still it will have more contact resistance. Then thin film batteries can be constructed in different 2D shapes and also can be extended to develop 3D shape. So with the same amount of material design, if you change 2D to 3D, it can improve the area is increased, you can improve the electrochemical. So these are the many advantages. Main is miniaturized. So this will be energy to provide energy for the miniaturized electronic devices, especially remote controlled electronic devices. So we have a 5 target thin film system. You can see that schematic diagram actually. So 5 targets and substrate. So you see that take the substrate first, okay, then substrate, then cathode collector, cathode material you put anode, okay, that one anode collector and cathode material you put, then electrolyte, then anode material. So you get a battery. So these anode and cathode collectors. So cathode, electrolyte, and anode. So batteries, thin film batteries. But since it is thin film, we will not keep like this. It will react. It is highly reactive with the surroundings. It changes its properties. So any thin film should be insulated. So finally, you make a insulating. So then its property will be intact. So this way you can get it. So 1, 2, 3, 4, 5. So you require 5 targets. So anode, cathode, electrolyte, leads, and this one is insulated. Leads and insulated. So you can get it. All 5 targets you can do. This system developed in our laboratory. It is a huge one actually. You can see for each one. Right? So you can do RF or one. And DC and okay. DC use any other material use RF. So these are what we did in bulk. So we did, you can see different colors, meaning is different sizes of nanoparticle section. Lithium manganese oxide. Lithium and titanate. So anode material. Different sizes. So different sizes mean different colors. Batteries for silver and equipment. The batteries, they are complete lab, different things, and these are our outputs. So not now actually they are match actually. And I think all my students they should acknowledge they did tremendous work and tremendous contribution. The knowledge into the lab developed fairly good nanoscience and nanotechnology lab. So these are the collaborators from various countries. Then the last one is very important one. Okay, I think I should acknowledge all the funding agencies, almost all the government funding agencies. They have funds up to 22 projects. And really without that, even though you have ideas and capabilities, without this, it is impossible to develop any laboratory. So, should highly thankful to various these things. And finally, so, okay, after my retirement, I have been awarded UGCPSR or faculty fellowship for 3 years to do continue my research, help the young minds in the field of nanoscience. Okay, thank you. So now, okay, we can ask some questions or anything of that kind. Hello? Hello?
Yes, sir. Yes, sir. Yes, sir. Participants, you can ask. Yes, you can unmute and you can ask, or you can type in the chat box. So there is a question, sir.
Yes, please.
Irmam Khan, he has asked to tell regarding stability of nano flowers and their application for cancer drug delivery. Shall I repeat?
It's simple. Yeah, no, I got it.
Yes.
I got it. See, for example, you have a like this. If actually they are highly stable. Okay, they are highly stable. It depends on the compound. If they are not stable, okay, they must be coated with nano coating with the insulating material. So we also do that. Reason is we also do that. Reason is I mentioned about this. You can see that, which is the one I will show you. Yes, yeah, actually. So here lithium cobalt oxide. Okay, when it is directly contact with the liquid electrolyte, liquid electrolyte will react with this one with the time. Electrolyte and electrode interface will get changed. So battery properties decreases very fast, changes very fast. To avoid this, what we do is actually we did the nano coatings, actually 2 to 3 nanometer size. 2 to 3 nanometer size if you coat, then okay, and still it has a force to move the ions, but your electrolyte will not interact with electrode material. So because of this nano size coating of the aluminum oxide, if the nano flow with the environment of the thing when you are going for drug discovery, so anything like that kind of. So in fact, what they do is actually they keep the drug in the form of a matrix. You know, matrix 2 by 2, 3 by 3, like this, like a tablet strip. You know, tablet strip. You 5 tablets, 2 lines, 2 by 2, 2 by n cross m matrix. You know, one tablet strip. Similar way, they fill the drug, and that will be in the nano size. And to this, one sensor is attached, and sensor and drug along with the battery in the form of nanopill. Actually, tomorrow I'll be talking about that. This pill will be, when swallowed through this mouth, it will go inside. Okay, sensor will sense wherever the tumor, cancer or anything of that kind. At that time, it will identify this movement of the pill will be run by the battery. Then wherever that is there, sensor will sense. When it comes, actually, that will get ejected. So medicine will be given exactly, or nanoparticles will be attached only to the cancer cell. Then with the laser, you just laser, you just expose it, then nanoparticle will get heated, then tumor will get destroyed. So that is the one through what we call as a nanopill, or we talk about nanotechnology, you know, right amount of medicine or nanoparticles at the right place. So that way, what happens actually, very less number of cells around the cancer cell will be destroyed. And regarding stability, your definitely if it is reactive with the surroundings, they do with what we call, I think, if I'm some what we call, I forgot this one, instead of insulating one, they they try to quote some, I forgot the word actually, because I am not, I have not done any drug delivery, but they quote actually to avoid any reaction with the nanoparticles. And those things actually, when they quote, no, so they will take care of the things actually. In battery, we quote actually, we quote insulating one. In fact, instead of using this chemical technique, if we use the ALD, 3 atomic layer actually, and that will be very, 170 times people have increased the capacity by taking the insulating material over the nanoparticle in atomic level. Through an atomic layer device, very costly, but one can do with that actually. Some chemistry, wet chemistry they try to cover the nanoparticle to avoid the interaction of the surroundings with the property will not be changed actually. But I have not done it in that, but similar way, they make it as like a tablet strip. They make it a matrix form, and that is connected to the sensor. Sensor will take care of wherever it is needed. That will be open. The medicine will be open, and our nanoparticle will be open. We untangle with the tumor. Afterwards, you expose with laser, then tumor will be killed. So that way, one can do, and stability also can be taken care of. And they will not send directly actually. Whereas in ordinary cancer time, no, you send the material. So doctor himself or herself will not know whether your medicine has gone to the exact place. But when it is going from this way, it kills the good cells also. The body gets weak. Radiation therapy when they do cancer people, so their body gets weak and become. But nanotechnology, when you use it, so I think body will not get weakened, and easily you can, the minimum amount of stability can be taken care of by entanglement of the chemicals. And that I have not done it, but okay, is it okay? Hello?
I think he has got the answer, sir. Is there any other question you can unmute and ask?
Or else we do for these things we do coatings actually. We do coatings. So similar fashion of this, actually we could go up to 1 or 2 or 3 nanometers. Afterwards, beyond that, it will not have much effect actually. But what happens, capacity will reduce actually. Effect means it's not used actually. It's not useful actually. If the insulating thickness is very high, so initial capacity drastically drops as possible thickness, just direct interaction of external things with your nanomaterial. We do this coating, the resin coating. I think so. Yes, here we have a good resin coating actually. This process we did actually, and many 3 nanometer size we did it. So this way it will be still better. That is a little chemistry you involve, and there is atom by atom you to it actually. So good control. But you need to have a good investment. Yes, cheapest is the chemical and this thing. Okay, bye. Anything?
Any other queries from the participant side?
They can send also anything to my email ID.
Sure, sir. Okay, sir. I think there is no more queries.
Okay, thank you.
Thank you, sir. Thank you for sharing your wonderful experience. I think the session would have opened many persons' eyes to start work on nanoscience, on batteries. Yes. Thank you, Paul.
Okay,
Yes, sir. You can stop sharing, sir.